Hey everyone, it's Dr. Garner here. In the last lesson, we learned about the structures of atoms. Those atoms are rarely found alone by themselves in nature. Instead, they're usually part of either molecules or part of extended networks. So, molecules are collections of atoms that are held together by chemical bonds. You can think of a molecule as being sort of one unit, one discrete unit of a substance. A familiar example of this would be water. Everyone knows that the formula for water is H2O. That describes the composition of one molecule of water. Each water molecule consists of one oxygen atom that's bonded by chemical bonds to two hydrogen atoms. So this would be one unit or one molecule of water. We have a couple of other examples of that here. Here we have ammonia, which has a molecular formula of NH3. So it contains a nitrogen atom that's bonded to three hydrogen atoms. This would be one unit of ammonia, one discrete unit of the substance. The last example that we have here is methane, or CH4. So again, one molecule of methane would contain one carbon atom attached to four hydrogen atoms. All right, so some substances tend to exist as molecules, whereas other substances instead exist as ionic networks. This is really common for substances that contain a combination of metals with nonmetals. Substances like this tend to form these extended ionic structures, whereas instead of having a discrete molecules with just a couple of atoms bound to each other, these substances tend to exist in repeating networks that extend repetitively in all directions. A good example of this would be sodium chloride or table salt. In sodium chloride, we don't have discrete molecules with one sodium attached to one chlorine. Instead, what we end up with is a repeating network like what you're seeing here, where sodium and chlorine ions are repeated over and over again indefinitely in all directions. So again, these extended networks tend to form whenever you have metals bonded to nonmetals, whereas these molecular structures tend to form whenever we have only nonmetals bonded with one another, so compounds containing only nonmetals. Whenever these molecules and ionic networks form, it's due to the rearrangement of electrons. So whenever we form molecules or extended ionic networks from individual atoms, that takes place due to the rearrangements of electrons to form those bonds that connect these atoms together. The nuclei do not change during this process. So whenever you have a chemical reaction where new bonds are being formed, the identities of the elements involved aren't changed because the nucleus doesn't change during that process. Right, molecules can be represented in a number of different ways, and we're going to show a few examples of that here on this slide. We're going to use an example of a molecule known as ribose. So ribose is the sugar that's found in the backbone of RNA, or ribonucleic acid. So this is an important biological molecule. Now, of course, the simplest way to represent the structure of a molecule would be to use its molecular formula. So the molecular formula is a formula that shows how many of each type of element are found within one molecule of that substance. So the molecular formula for ribose is C5H10O5. What that signifies is that one molecule, or one unit of ribose, contains 5 carbon atoms, 10 hydrogen atoms, and 5 oxygen atoms. Right, so that gives us some information about the structure of ribose, but it doesn't tell us how those atoms are actually connected to each other. For that, we can instead use what we call a structural formula. The structural formula shows how all of the atoms in the molecule are bonded together with one another. So from the molecular formula, we knew how many of each type of atom we had, but we didn't know how they were connected together. And from the structural formula, you can see how all of those atoms are connected. In fact, you can see that there's this 5-membered ring at the heart of the ribose molecule. And again, you wouldn't have known necessarily that that was there just by looking at the molecular formula. I do want to go ahead and introduce what these thick wedged lines represent, as well as these dashed lines. These lines are an attempt to show three-dimensionality in this structure. This wedged line represents that the carbon at the thick end of the line is coming out of the screen at us. The dashed line shows the reverse of that. The dashed line shows that the hydrogen at the thick end of that dashed line is going into the plane of the screen away from you. So these are one way of showing three-dimensionality in these two-dimensional structural formulas. Of course, another way of showing three-dimensionality would be to use a computer model to represent a structure of this molecule. And there are a few different ways of doing that. One common style that's used to represent the 3D structures of molecules are these ball and stick models. These ball and stick models represent atoms as small spheres that are connected by sticks that represent the chemical bonds that connect the atoms. So you can see here a 3D model representing ribose. Now, this is not the only style of 3D model that's used to represent molecules. Another commonly encountered style is the space-filling model. Space-filling models more accurately model the actual volume of space that's occupied by each atom's electron cloud, and they give you a better idea of the actual size and the actual volume that's occupied by the electrons in this model, in this molecule. So as you can see in the ball and stick model, it's kind of easy to look at this molecule. It's easy to see where all the atoms are, but it doesn't give you a realistic view of how much space is actually filled in the structure. From the space-filling model, you can see this is a much more solid object than the ball and stick model implies. All right, so on this slide, I want to try to connect grams, which are, of course, how we measure mass on the macro scale, to the atomic mass units that we learned about in the last lesson. In the last lesson, we defined this new quantity of mass, or this new unit of mass, known as an atomic mass unit, or AMU. And we saw that this unit, the AMU, is approximately equal to the mass of a proton or a neutron. And we saw that it's approximately equal to 1.66 times 10 to the negative 24 grams. So this is an exceedingly small unit of mass. We use it to measure the masses of individual atoms and of individual subatomic particles. But in terms of everyday amounts of mass, this is extremely small. Now we can take this equation and invert it. If we divide both sides of this equation by this value here, we can solve for what 1 gram equals in terms of atomic mass units. So if you do that, you get something like this. 1 gram is equal to 6.022 times 10 to the 23 atomic mass units. Now this number might look familiar if you've had high school chemistry. This number is also known as Avogadro's number. So Avogadro's number, which you'll sometimes see abbreviated with this capital N with a subscript capital A next to it, again has this value of 6.022 times 10 to the 23. This value, Avogadro's number, is used as the basis of defining a new unit known as a mole. 1 mole is a collection that contains Avogadro's number of objects. So what those objects are, it just depends on what you're counting. So 1 mole might be Avogadro's number of atoms, 1 mole might be Avogadro's number of molecules, whatever it is you're interested in counting. So you can think of Avogadro's number as having units of inverse moles, or more accurately, units of whatever it is you're counting per mole of whatever it is you're counting. So for example, atoms per mole of atoms might be your units for Avogadro's number if you're interested in counting atoms. The idea of a mole is analogous to the idea of a dozen. So 1 dozen is a collection of 12 objects. By the same logic, 1 mole is a collection of Avogadro's number of objects. And the math that involves converting between number of objects and moles is the same as the math that you would use to convert between dozens and numbers of objects. So we have just a couple of examples here showing this. So in this first example, we're asked how many donuts are in 5 dozen donuts. So intuitively, we all know how to solve this problem. We know that we need to take 5 dozen and multiply it by 12, since there are 12 donuts per dozen donuts. So if we multiply these values together, our units of dozen here are going to cancel out, and we're going to end up with 60 donuts. Now, the problem below it is exactly the same. We're being asked how many atoms are in 5 moles of atoms. The way that you would solve this problem is exactly the same as how you would solve the problem above it. We would take our 5 moles of atoms, and we would multiply by the number of atoms per mole of atoms. So we would multiply by Avogadro's number, just like we multiplied by 12 before. So 5 moles times Avogadro's number of atoms per mole. My units of moles are going to cancel out, and I'm going to end up with 3.011 times 10 to the 24 atoms. All right. This slide starts with the sentence, a mole of atoms are contained within a sample weighing the same number of grams as its atomic mass in AMU. All right, this is a fairly dense sentence, so let's take a moment and try to unpack what this sentence is trying to say. So let's look at an example first where we have a carbon atom. 1 carbon atom, on average, has a mass of about 12.011 atomic mass units. So this is the number from the periodic table. The atomic weight of carbon is 12.011. So what that tells us is that an average carbon atom has a mass of 12.011 atomic mass units. All All right, so if you have a collection of Avogadro's number of carbon atoms, again, that's going to be the same as 1 mole of carbon atoms, just like 12 of something would be equal to a dozen. So if you have 1 mole of carbon atoms, that's going to have a mass of 12.011 grams. So again, as the sentence up here is saying, a mole of atoms, which we have here, is going to have a mass that's equal to the atomic mass of the substance, but with units of grams. So 1 mole of carbon would have a mass of about 12 grams. So in other words, that number on the periodic table, you can think of that as either being the mass of an individual atom in units of AMU, or you could think of it as being the mass of 1 mole of an atom in units of grams. So you can think of that number on the periodic table as either having units of AMU or units of grams per mole of material, whichever is more convenient for the math that you're doing. And we can apply this same concept to molecules as well. So for example, if we look back at ribose again, if we had 1 mole of ribose molecules, that collection of ribose molecules would have a mass of about 150 grams. And again, since it's a mole of molecules, it would have a total of Avogadro's number of molecules in that collection. Let's see if we can figure out where this number 150 comes from. So this simply comes from taking the masses of each of the atoms in this molecule and adding up their masses. So for example, if I had 1 mole of ribose molecules, that means that I'm going to have 5 moles of carbon atoms, since there are 5 carbon atoms in every molecule of ribose. So if I have 1 mole of ribose, I'm going to have 5 moles of carbon atoms. So if I want to know the mass of those carbon atoms, I could take my 5 moles of carbon atoms and multiply it by that atomic weight of carbon. So as we just saw a moment ago, 1 mole of carbon has a mass of about 12 grams. So I could just multiply by that ratio, 12 grams of carbon per mole. If I do that, my units of moles are going to cancel out, and I'm going to be left with about 60 grams. So what that tells me is that if I had a mole of ribose, that sample of ribose would contain 60 grams of carbon. So I just need to do the same thing now for the other 2 elements to figure out the total mass of this sample of ribose. So if I had 1 mole of ribose molecules, each of those molecules contains 10 hydrogen atoms. So that means that I'm going to have 10 moles of hydrogen atoms. So I can do the same thing there. I can multiply by the atomic weight of hydrogen, which is about 1.008 grams per mole. I just rounded off a little bit here. So if I multiply these values together, my moles are going to cancel out, and I'm going to end up with about 10 grams of hydrogen. So again, that 1 mole sample of ribose that I had contained a total of 10 grams of hydrogen. We could do the same thing now finally with the oxygen. So if I have 1 mole of ribose molecules, each molecule possesses 5 atoms of oxygen. So that means that that sample contains 5 moles of oxygen atoms. So I could do the same thing here. I can multiply by the atomic weight of oxygen off of the periodic table. So its atomic weight is approximately 16 grams per mole. So if I do this, my moles are going to cancel out. I'm going to be left with units of grams. This comes out to about 80 grams. So now I can just add together the masses of each of these elements that's found in ribose, and it adds up to about 150 grams. This quantity is known as the molar mass of this molecule. It's the mass of 1 mole of the substance. You'll also hear this value referred to as the molecular weight. So these 2 terms, molar mass and molecular weight, are used interchangeably to refer to the same value. And you'll often see this mass represented not just in units of grams, but in units of grams per mole. So you'll see it both ways depending on the context. All right, so we can relate the mass, the number of moles of the substance, and the number of particles, and by particles I either mean atoms, molecules, whatever it is you're counting, using Avogadro's number and the molar mass that we just learned about. So let's take a look at how all these quantities are related. So if I know the mass of a material, I can figure out how many moles of material I have by taking that mass and dividing it by the molecular weight or the molar mass of the substance. I can go in reverse as well. If I have the moles of a material, I can multiply by molar mass to find the grams or the mass of that material. If I'm interested in figuring out how many atoms or how many molecules are in a substance, I can take the moles of that substance or the moles of atoms and multiply by Avogadro's number to get the number of atoms. I can go in reverse as well. If I know the number of atoms or the number of molecules, I can divide by Avogadro's number in order to figure out how many moles of that material I have. It's important to be comfortable using each of these conversions. You're going to be using these fairly regularly throughout the semester, especially the conversion between moles and grams. It's important to get used to doing these. All right, let's take a look at an example of a problem like this. In this question, we're being asked to determine the mass of 2.3 moles of ammonia, and we're given the formula here for ammonia as being NH3. All right, so if we go back to that last slide, we're trying to convert between moles and mass. So it looks like our connection between those two quantities is the molar mass. So I need to start this problem by figuring out my molar mass of ammonia. All right, so just like we did for ribose, I can figure out my molar mass by simply adding together the masses of all of the atoms that are found in this molecule. So I can take my 1 atom of nitrogen and multiply that by the atomic weight of nitrogen, which is about 14 grams per mole. Then I can add to that my 3 hydrogen atoms, times the atomic weight of hydrogen, which is about 1.008 grams per mole. If I add those two values together, I'm going to get the overall molar mass, which is 17.03 grams per mole. All right, so now that I know my molar mass, I can use that to convert from moles into mass of material. So just like we saw in that last slide, I can take my moles of material, 2.3 moles, and multiply it by that molar mass that I just found. And notice that the units work out here. So if I have moles times grams per mole, the moles are going to cancel out with one another, and I'm going to be left just with units of grams. So rather than memorizing that chart from the last slide, I would encourage you to work out these problems using dimensional analysis. Decide whether to multiply or divide based on the types of units that you have and what you need to do to cancel out those units to get the units that you'd like to end up with. So in this case, we're going to end up with grams. If I multiply these two values together, I'm going to get about 39 grams. So 2.3 moles of ammonia molecules will have a mass of about 39 grams. All right, let's try out a practice problem here. And as usual, I would encourage you to pause the video and try this problem out on your own first. Once you've got it, unpause and take a look at the solution. All right, so in this question, we're being asked how many moles are in 3.4 grams of phosphorus trifluoride, so PF3. All right, so again, we're trying to convert between mass and moles. And just like in that last problem, the connection between those two quantities is the molar mass. So we want to start this problem by figuring out the molar mass of phosphorus trifluoride. All right, so we can do that, of course, by taking the number of each atom that we have, multiplying it by the atomic weight of that element, and adding those quantities together. So let's start with the phosphorus. We have 1 atom of phosphorus, so I'll put that down here. If we go to the periodic table, phosphorus has an atomic weight of about 30.97 grams per mole. So that's the phosphorus. We're going to add that to the mass now of the fluorine. So we have 3 atoms of fluorine. And overall, from the periodic table, you'll see that they have a mass of about 19 grams per mole. So if we add these two values together, we're going to end up with about 87.97 grams per mole. So that's our molar mass of phosphorus trifluoride. All right, so now we need to take the mass that we're given and combine that in some way with our molar mass such that we get units of grams. Again, we want to get units of moles. So we want to cancel out our units of grams here, and we need to end up with units of moles. So in order to do that, we can take our 3.4 grams and divide by the molar mass. So if we do that, our grams are going to cancel out on top and bottom, and we're going to end up with units of 1 over inverse moles. And of course, that just simplifies to simply be moles. So the grams cancel, and I end up with units of moles. And if I work out the math here, I get a value of 0.039 moles. So that gives me answer choice C for this question. All right, we'll stop there for this video. Thank you for watching.